Okay, welcome back everybody after the lunch. I hope you all had a delicious lunch. If you guys or if anybody has not collected their drink voucher, please do so at the reception of the conference. Has anybody not received a drink voucher? Yeah, don't forget that outside. Okay, the next speaker we have is Hendrik Heuer, and he's going to talk about hacking human language. So give him a hand.
Thank you for the introduction. And this is another talk with a very pretentious title, so I called it Hacking Human Language. But I'm not talking about this kind of hacking. I really like the hacker ethics. I don't know if anybody of you knows this. And one part of this says that the access to computers and anything which might teach you something about the way the world works should be unlimited and total. And then there's also this part on to always yield to the hands-on imperative, which basically means learning by doing. And I'm working on my master's thesis right now on natural language processing, and I think it's quite interesting, so I wanted to share that. So the agenda for today is to talk a bit about computational social science and what that is, then have a brief intro to natural language processing, which will relate to the keynote we saw today. And then I'm going to talk about word vector representations, and I'm going to visualize my own Google searches. So the big picture, and I really love this slide because it just looks like a map of Europe, right? But this map was plotted just by doing one pixel for the GPS coordinates of tens of millions of Flickr photos. So just by plotting them, you get the entire map of Europe, and you see some parts like England are much more crowded than others. But the funny thing is, if you also look at the text in the Flickr photos, then you can also get a real city guide. So you get the cathedral in Cologne or the London Eye. So I'm really fascinated by how much information about the world you get from this big data. So talking about computational social science, which is also sometimes called digital humanities. So the idea here is to combine computer science and the techniques from computer science with social science. And this makes new, really interesting research possible. So you can, for instance, analyze massive social networks, or you can analyze the content of millions of books. And I actually analyzed my own Gmail correspondence with this immersion project from MIT Media Lab. So I took 27,574 mails and 222 people in there, and you can see the green ones are my friends from university back in Germany, the orange ones are my friends here in Sweden, and the blue part is my family. You can also get it with your names, but I didn't put in the names here. So another interesting paper I quickly want to show you is this paper called Massive Scaled Automated Analysis of News Content. And there they took 2.5 million articles, more than any human could possibly read, and automatically annotated that into 15 different topic areas like fashion, art, politics, and science. And then they looked and compared it in regards to readability, linguistic subjectivity, and gender imbalances, and I'm going to show you what that means. But for instance, talking about linguistic subjectivity, there you look at the adjectives with a technique called part-of-speech tagging, which I'm going to show you in a minute. And then there is a corpus called the Senti word net. And there, for instance, you have a word like humor, which is a very positive word, or hate, which is a very negative word. And based on that, they just looked how strong are the emotions associated with the adjectives used, and how many adjectives. And it's very interesting, because you see that in fashion, the linguistic subjectivity is quite high, whereas in politics, the election reporting, or in business, it's quite low. So they hypothesize, they can't prove it, but they have an indication that the low level of political interest and engagement might as well be connected to the lack of subjectivity, because they think it might be less readable. Another really interesting research, and this again is on 2.5 million articles, is looking at the male to female ratio. For this, they used a technique called named entity recognition. So you find names like Hendrik, and associate it with a gender. And if you do this, you can see which topics are more male-biased and are less male-biased. And it's quite shocking, because if you look at sports, so here, the more to the right, the more biased. So sports is incredibly biased, and there's not much reporting about females in sports. And I think this is very interesting, and fashion is the only topic where it's almost even. So taking a step back, because for me, doing data science and analytics is a bit like playing Lego, because you're just combining building blocks. So you have tools for text processing, like the natural language toolkit, this word-to-vec approach, and spaCy. Then, of course, you do visualization with different JavaScript libraries. You can do topic modeling with gensim, and you can do machine learning with scikit-learn. And I'm going to show you a bit what to do with that. But these are really the building blocks, and you basically just need to learn how to combine them. So giving you a small introduction to natural language processing. For me, a good starting point is this O'Reilly book, which you can actually read for free on nltk.org/book. It's a great resource to start with, a lot of tutorials. It's well documented, and it also comes with a lot of corpora, so it's data to play with. One of the most fundamental things you have to do is splitting a sentence into single words, which is called word tokenization. And as you can see, it's just 2 lines, and then you have a list which you can manipulate. The next step is, of course, splitting a sentence. And if you look at this, it's quite interesting, because you can't just split it with the words, you can still split it by the space. But here, if you would split it by the dot, you wouldn't get the comma and all the other words. And of course, it would misclassify this. So this is a bit of a harder problem, but again, in Python, just 2 lines. And you can also do this for Swedish. So you just load this, and then you use these functions and tokenize. Next problem, if you're running a search engine like Google, you might not want to differentiate between the past of a word and the present form of a word. So you use a technique called stemming, where you find the root form of a word. And there are different approaches, and some are better for some applications and some are better for others. So for instance, women is getting shortened to wom, which might be good for your application or not. The next problem, and we just talked about this, is the part of speech tagging. And you might all remember this from school. It's like, this is a noun, this is a verb. And again, this is quite easy. As you can see, it can tell these are nouns, these are verbs, and these are adjectives. And you see the wildcard, because it also tries to tell this is a singular noun and this is a plural noun. But you can also see it's not really clear cut, and it's not that good. So usually I just look at the first 2. But to tell nouns, verbs, and adjectives apart, this is a really good resource. The next step is the named entity recognition. So if you want to identify these are people, these are organizations or locations, you can also do this very easily. Again, just 2 lines if you put it in 2 lines. And here you can see it recognized New York City as a geopolitical entity. You might ask why it's not Stockholm, because it didn't work. So again, this is, I don't know why it's that bad, but for this example, it actually worked. But there are definitely data sets you can use where Stockholm will be recognized as well. The next problem you might encounter if you do natural language processing is sentiment analysis, and that's telling if a sentence is positive or negative. So the sentence in this case is, this film doesn't care about cleverness, wit, or any other kind of intelligent humor. And just looking at the words, they're quite positive. So you see here in the tagging, humor has 2 pluses, very positive word. Intelligence is positive, cleverness. So just by looking at the words and counting them and counting the individual sentiment, it doesn't get you that far, because this is an insanely bad sentence, a really harsh critique. And for this, they actually use the recursive deep neural network, which Rolf was talking about. And if you want to use this, I would just recommend using this Stanford Core NLP tool, which is written in Java, but you can use the subprocess module in Python and just get the results from that. But now we're going to the main part of this talk, which is the vector representation, and that's hopefully giving you an idea about linguistics. So this is a very famous quote: "You shall know a word by the company it keeps," by Firth in 1957 already. And it's one of the most successful ideas of modern statistical natural language processing. And it's very, very simple. It's basically saying that the word banking is similar as a topic to the word it co-occurs with. And this is coincidental, co-occurs with crisis, but also with debt and problems. So if you have enough examples of a word like banking, you can get a feeling what it means. And using this and just looking at a word in its context, you can get a vector representation of the word. So remembering from school, a vector is just the direction in space, and I'm using three-dimensional ones because these are the ones you're most familiar with. Actually, in practice, we're using much higher dimensional ones. So in this particular one, I'm using 300-dimensional vectors. But the idea is basically representing a word by a vector, so just a bunch of numbers, just a direction in space, and then there are very different ways to compute this. There's word2vec, which was introduced by a paper from Google in 2013. There are also dependency-based word embeddings, and there's random indexing, and I'm going to talk a bit about that. But why would you want to represent the word with a vector? It's not that exciting. Well, the exciting thing is that if you look at that, and again, it's just directions in space, nothing fancy, but the direction from the vector, from the point for men and the point for women, is almost the same to the one from uncle to aunt and from king to queen. So they encode semantic relationships. So this could be called femaleness. Another one could be plural, so the one from king to kings and queen to queens is very similar. And because it's just math, you can just manipulate this and even solve these puzzles. So you can ask the system, so the word man is to woman as king is to what other word? And these are very simple intelligence test questions. So a lot of people got really excited about these techniques. It's not just about simple relationships either. So you have, for instance, a vector that represents the is capital city of relationship. So the one going from Germany to Berlin is similar to the one from Portugal to Lisbon. Not exactly, as you can see, but it's quite helpful. And you do this nearest neighbor search, and it gets you quite far. Another interesting thing is, again, these are directions, so you can also look for similar vectors. And if you do this with Sweden, then you actually end up with the Nordic countries being the most similar, so the name of other Nordic countries. Another interesting thing that initially quite confused me was that the floorball federation was quite high. So I looked that up. And apparently it's a sport developed in Sweden in the 1970s, and it's most popular where it was developed. So it is a noun closely connected, or maybe uniquely connected to Sweden. Also, I trained this on a relatively small data set. That might also be part of the problem. But another interesting thing you can learn from is that, for instance, Swedish as an adjective, which theoretically is very close to Sweden, is ranked below Helsinki-Vantaa. So Helsinki-Vantaa is the place in Helsinki where the airport is. So my professor and my theory is that it's because a lot of people travel from Stockholm, Sweden to Helsinki-Vantaa. And what this got right is that structurally, Swedish is not very similar to Sweden because Swedish is an adjective, while Sweden is a property. Vantaa, on the other hand, is also a place, just like Sweden. Here's another example. For instance, looking at Harvard, you get other Ivy League schools like Yale. You get the concept Professor McGill, which is in Canada. So you get a feeling it's not incredibly structured, but there's definitely something interesting to this. So just to wrap this up conceptually, what we want on the left is a vector representing a word like linguistics, and on the right, we're using a neural network. So talking about using this in Python, gensim was already mentioned today, It makes it incredibly easy. It's really a lot of fun to use this, and you can actually find pre-trained vectors, just like Olaf used the pre-trained neural network for deep learning. So what this is doing, it's implementing this paper from 2013 from Nikolov and others at Google. An alternative is another Python library called spaCy, which is using a different approach. And you find the links, and I'm going to share the presentation with you, of course. And here, they also take the sentence structure. So this is a noun, this is a verb, which we don't say explicitly in the word2vec. It kind of emerges, but it's not explicitly taking into account when computing it. So let's just compare the results, because if you do different training approaches, you get different vectors. And just some context, the two on the left is this gensim word2vec. And the one on the right is the one that takes also, this is a noun, this is an adjective into account. Looking on top, we have the back of words 2. This is both different approaches. Because word2vec is basically a tool which implements many more ways of computing it. But if we talk about back of words 2, we're actually taking the two words from the left and the two words from the right into account. If we do back of words 5, we're taking context window of 5. And if you do this, you end up with the most similar words. And this is quite interesting again. If you put in the word Florida for the word2vec, the back of words, you end up with cities in the state of Florida. If you also take the role in the sentence into account, you end up with other sentences like Texas, Louisiana, and California. The same and even more interesting with Harry Potter. So if you do it with Harry Potter, with this context window, just looking at the 5 words to the left and the 5 words to the right, you get Snape, you get Malfoy, so characters from the Harry Potter universe. Whereas if you also take the sentence structure into account, you end up with, for instance, Sunnydale from the Buffy the Vampire Slayer universe, which is another school. So that's quite interesting. So if you don't, you can compute the vectors yourself, but you can also download pre-trained vectors, which were pre-trained by Google on 100 billion words. So that would take you quite a while. So you can just use them, but they're quite big. But again, why would you use this? Why is this interesting? Talking a bit about applications. And my favorite application for this is basically machine translation. I think I'm just really fascinated by this. So again, this just looks at the structure of language and tries to find a vector. And if we, for instance, take the English Wikipedia to learn the English words and the Spanish Wikipedia to learn the Spanish words, then you can say, okay, give me the word for cow in English. Then you have a vector, just a direction in space. Then you go to the other vector space, which you trained on the Spanish words, and say, okay, in this direction, in this space, what is closest to it? And it happens to be that it is the word, the Spanish word for cow. So that's really cool. Another thing I've been using this is to compare big text sources. So for this talk, what I actually did is I compared my own Google searches. So you can go here on Google and just download all your searches, and you get a bunch of JSON files for different times. And it might look a lot like this. So these are just search terms, me searching for hoverboard. It's just a JSON file. And then I'm doing the 3 following things. For all the words I searched for, I'm finding this vector representation. Then I'm doing dimensionality reduction. And I'm going to output this in JSON to have it as a website. So to find the word representation, again, it's very, very easy. You just use gensim and some vectors you have pre-trained. And on the gensim side, they definitely tell you how to train it yourself. But then it's just really, you go through the words you have, and if your word is in the model, because not all words are in the model, then, for instance, here you print it out. So a bigger example, where I'm also keeping track of the most frequent words, because they're not that interesting. I'm just collecting the vectors in a list, and then I'm returning this list, because again, what I want is just this, a vector, a numerical representation of the words. But now, I have this high dimension of vectors, so 300 dimensional. So what am I going to do with it? One approach is dimensionality reduction. And the idea here is just to take this huge vector and find a point in space, a two-dimensional vector, technically. And the interesting thing here is, if you do it with TSNE, also with PCA, then similar words will be close to each other. So I'm going to show you in a minute how this looks like in the big picture, so stay tuned. Just one thing before that, to compute it, again, thanks to the awesome scikit-learn library, is incredibly easy. It's basically just 2 lines where you say, okay, I want two-dimensional vectors. Okay, I'm fixing the random state so I can compare my results. And then you just do fit transform with scikit-learn, and this returns two-dimensional vectors. And then the next step is just writing it out to JSON. So the idea here is, for instance, to be able to use this D3JS library, which is a lot of fun. So this is precisely what I did. So here are my Google searches. The red ones are from October to December 2014, when I was living here in Stockholm. July to September 2011 are orange, and I was living in the United States. And the yellow colored one are the ones I searched for in both. So you see similar words get encoded similarly to each other. So bass is close to guitar. And because of the dimensionality reduction, guitar theoretically should be on top of each other, so they should have the exact same coordinates. That's not the case, but I think that's because of the dimensionality reduction. So this is not that interesting, but if you start looking at places, for instance, all the place words I Googled are encoded similarly. So you have the Canadian cities next to each other, you have Portland, you have Amsterdam, Stockholm, and you can see some I only Googled in 2014, some I Googled in both cases. So this is a nice way of comparing text sources, and I'm actually, for my master thesis, I'm using this to compare books to book summaries. So this is the big picture. This is like the global context, because the dimensionality reduction not only makes sure that similar words end up being similar to close to each other, but also has like a global idea. And it's not always perfect, because KTH is very close to lazy. I don't know if you can see this. It's of course not the case. But here's another example. So philosophy and Hegel and Stanford and Oxford, they end up close together. And developer and Linux and Apple, they're closer together than some people might think. And Richard Stallman, for instance, also sneaked in there close to developer. So thanks so much for your attention. You can find the slides starting now on tinyurl PyCon -word2vec. And yeah, I'm looking forward to your questions. Thanks.
Hi.
Hey.
You showed that when you're doing like the tokenizer, you have one tokenizer for English and one for Swedish. I assume in your own data set, being an international person, that like in your search, you're searching for words both in English and Swedish and German. Is there any ways to deal with this multi-language data set in general?
I'm not sure. I think I know how to train my own corpus, so I guess I could just make a big corpus with German and English. I'm German, so I could have done that. In this particular case, I did this if in model and then just threw the ones away, so the German words just went away. But probably you can account for that, yeah. You can train with your own corpus, so if you, yeah.
Another quick language question. Is there, for that like Swedish tokenizer, does that also handle things like stemming and parts of speech, or is there not the same support as there is for English for those types of
It very much depends on the language, but you can just Google for it, and there are like a lot of people working on it, and NLTK is quite broadly supported in my perception, so there should be something for other languages.
Thanks.
So I just have one question. How do you go from like vectors for each word to actually classifying, like, for instance, documents?
There's been work on that. I think it's kind of the next frontier. And actually, if you look into gensim, there is a doc2vec where they're using a similar approach. But I would say that's like where the research is right now. You can already use it with doc2vec. It's not as trivial as just like summing them up. You can get some results with it. But yeah, there's been active work on it. Actually, maybe Roloff knows more. He might be working on that right now.
I'm wondering about this clustering dimensionality reduction algorithm that you use. Is it usually used for this kind of endeavor, or what is special about it? I mean, why don't MDS or something more classical?
So the good thing, this is based on probability distribution. So there's this Kuller-Leibler divergence, so between two probability distribution, and that is like making sure that similar words stay similar to each other and distant words get distance from each other. So you can use it for a lot of different things. I just looked into it. For me, it worked better than principal component analysis, and I've seen a lot of other people using it as well, and so I just went with it, and it worked quite well for me.
Okay, great.
Most of other articles on this topic usually deal with either examples in Romanic or Germanic languages. But the question is, does it work, and how, for, say, Slavic languages or Finnish or even Hindi, I don't know, or any languages that are quite far in their linguistic structure from Romanic and Germanic? Thanks.
Yeah, sure. So morphologically rich languages like Finnish or languages with a suffix, they're not like as perfectly made for this model, but our professor is using a technology in his startup, Gavagai, where they also support Finnish and I think also Russian, and they don't use this technique, but they have a similar one based on vectors. So I think in theory you can use that for any language.
Yes, I was wondering, what would you say is the main benefit of using, say, Python for this kind of research rather than any other language or frameworks available?
Yeah, good that you say that. But what I'm insanely happy about with this is just the master thesis work. I'm just a master student in KTH. Is that a lot of researchers who are doing cutting-edge research are sharing it, so I can play with it and actually do applications with it, and the infrastructure for Python is just insanely good. So, like, especially with gensim, if you train the word-to-vec vectors with gensim, that's faster than C in Python because it's so well optimized by Hendrik Heuer, if I'm saying it right. So, like, check out his blog. It's really, really impressive what he pulls off with Python. So, yeah.
Okay, thank you, Hendrik. Thank you so much.